Hello everyone! Today we are going to do a quick little crash course on soil. So these are really important things to know if you're going to be looking at soil tests or if you're just going to be talking about soil with people who might know a little bit more than you or might know a little bit less than you. So it's really good to know these things just to kind of have easier conversations surrounding soil. Starting off hot with what is soil? So it is made up of about 5% organic matter, 45% mineral matter, which is sand, silt, and clay, 50% water and air. And these ratios do change. Some soils will have a little bit more organic matter. 5% is about the standard. But everything on Earth starts with soil. It grows the plants that you eat, it feeds the animals that you eat, it filters the water that we drink, it stores the carbon that we breathe, and it is the habitat of many animals, like worms and that sort of stuff. So, right off the bat, we're going to talk about soil horizons. So, soil horizons are the different layers in the soil profile that you see when you dig around. So, this photo is of a soil pit that we dug actually right by our site here in Birch Hills. And you can see three really distinct layers. So, these are the A, B, and C horizons. A is the top, B is the middle, C is the bottom. So the A horizon is typically a darker black color. The B horizon will be a little bit lighter brown. And then the C horizon is also known as parent material. And that will usually be a little bit of a lighter gray or a lighter brown color. So there are other types of soil that don't follow the general rule of A, B, and C horizons, including forest soils that just have a leaf litter layer and no distinct A horizon. Peat bogs that can sometimes have more than a meter of decomposing organic matter, or soils along river floodplains, in sand dunes, on the tops of hills that don't have a B horizon and are just A and C horizons that are usually combined through the process of tillage. So now that we know what the horizons are, let's talk about soil texture. So soil texture is the relative proportion of sand, silt, and clay particles in a soil. It can't be easily changed, as this is one of the permanent characteristics of soils. So you can change the soil structure, but you cannot change the soil texture. I always like to say it took 17,000 years for the soils in Saskatchewan to be created. It's not going to change overnight. Sandy soils are considered coarse, and silty and clayey soils are considered fine textured soils. So on the right of the screen here, you have the soil textural triangle. And depending on the percentage of sand, silt, and clay in the soil, that determines what the texture is. So you can see there's clay, clay loam, loam, silty clay loam, sandy clay loam. There's essentially endless combinations of these three minerals. So sand particles are larger than clay particles, so they have less surface area, and this leads to better water infiltration. Think of when you're building a sandcastle, you pour water into the sand and it just goes right through. That is because it has less surface area and the water just keeps getting pulled down by gravity. But as you can also tell, it has poor water retention. So it's going to get wet, but it's not going to keep the water there. Like it's just going to flow right down. So you can usually tell what type of soil you're working with just by mixing it with a bit of water and feeling it in your hands. So you can have a little thing of water, a little thing of soil, add some water, and then you can feel it like that. If it feels gritty or smooth, that'll determine, it can help you determine the relative proportions of sand, silt, or clay, and then you can determine what texture your soil is. So soil structure is how the soil particles are arranged. And these are called aggregates. Sometimes they're called PEDs, but aggregates are the more common term. The aggregates are held together by organic matter and microbial exudates, basically just goop that the microbes produce. And then it creates all these little soil particles will go together, and then you have a little aggregate. So the structure determines how much air and water are present in the soil and how easily plant roots can grow through it. So soil structure can be changed, unlike soil texture, And it can be improved through reducing tillage, adding compost, planting cover crops, and using biological soil amendments. So you can see on the left-hand side of the screen, there are 4 different soil structure types. There's blocky, prismatic, granular, and platy or massive. So prismatic and granular are kind of the best, quote unquote, soil structures that you can have for water movement, root growth, all of that good stuff. Soils with a platy or massive or blocky structure usually have poor water infiltration and can be a result of compaction and tillage. Granular soils don't have many aggregates and tend to have a little bit of a higher erosion risk. So there are many other soil structures other than these 4. These include columnar, which look like prismatic, but they have a salty cap on top that are impenetrable. So that's not a good thing. There's single grain, which is even smaller than granular, wedge and lenticular, which are similar to the platy structure, but they're a little bit smaller. And then there's spheroidal, which is basically just like your soil is creating marbles, think of. That's kind of a good comparison. So soil and water. Everyone knows that you need water to grow plants, but soils also need water to function. Water allows microbes to move around, nutrients to move around, all of that good stuff. Too much water, actually, though, is a bad thing. It will fill all of the pores and cracks with water, leaving no room for air and resulting in standing water and anaerobic soil. Anaerobic just means no oxygen. On the other hand, not enough water will cause the soil to dry up and crack, and this makes it more difficult for the water to be absorbed during the next moisture event. So this is called permanent wilting point, and it is when the soil is so dry that there is no water left for plants to take up, and then the plants start to wilt, and it's basically past the point of no return. So the Goldilocks water level is called field capacity, and it is how much water a soil can hold after gravity has drained all the excess water away. And so field capacity is perfect because there's still oxygen in the pores, there's water in the pores, the plants aren't wilting, but they're also not drowning. So water movement can happen in a couple different ways throughout the soil. There is infiltration, and this is also kind of called percolation. It is the water movement through the pores and cracks until the soil is saturated. There's gravitational flow, which is when the soil is saturated, gravity will pull the extra water downward through the larger pores. Capillary flow, also called capillary action, sometimes pronounced capillary. This is in soils that are at field capacity. The water moves in all directions through adhesion and cohesion. So adhesion is water to soil, and cohesion is water to water, essentially defying gravity. So it can move up, it can move to the side, every way. There's redistribution, which is water moving from wetter areas to drier areas. And then this also goes hand in hand with evaporation. So water will move from lower in the soil profile up higher and then will evaporate because that topsoil is drier. I think fertilizers are a pretty common thing that people know about. I won't get into fertility application or anything like that. But there is actually usually a base amount of macro and micronutrients in the soil. So there's NPK and S, nitrogen, phosphorus, potassium, and sulfur. And there's usually a base amount of that in the soil, whether you apply fertilizer or not. And these levels come from decomposing plant matter, both decomposing soil animals and living soil animals. Think of worm castings, and then parent materials breaking down. So that's sea horizon being broken down and releasing the minerals that it contains up higher into the soil profile for the plants to use. Finally, this is my favorite part of soil, is the soil chemistry. So there are a few lesser known chem terms that come up when talking about soil, especially in the context of a soil sample report. So there's a lot of jargon, I guess you could say, in a soil report that you might not be familiar with. So this can kind of help you get a grasp of what those soil reports are talking about. First up, we're gonna it's kind of easy, but ions are a group of atoms that have a neutral charge. So think of H2O. There's 2 hydrogens, 1 oxygen. Yeah. And there's no charge. Cations are positively charged particles such as hydrogen, and anions are negatively charged particles such as chlorine. Next up, we have organic matter, which is actually an anion. It has a negative charge. And organic matter is made from the decomposition of dead plants and animals. It improves soil structure, not texture, soil structure, increases water retention, provides and holds nutrients, and supports life in the soil. Next up, we are getting a little bit more complicated, CEC, which is cation exchange capacity. And the CEC is a soil's ability to hold and exchange positively charged elements. And so opposites attract, think of magnets. This is directly related to how many negatively charged particles are in the soil. So clay and organic matter are both negatively charged, so they can both bind to these cations quite well. The more clay and organic matter that are in the soil, the higher the CEC value will be. And CEC is measured in milliequivalents per 100 grams of soil, which is basically just a nothing value. If you understand it, that's great. You don't really have to understand it to know higher is better. So these values typically range from 1 to 400. Pure beach sand has no clay in it, so there's no organic matter, no clay, no negative charge. So the CEC value is like 1 to 5. On the other hand, pure organic matter, which is basically 100% negative ions or anions, it has a CEC value of 200 to 400. So that is a huge difference between those two different types of particles, I guess. There's a few different types of clay. I won't get into that, but depending on the type of clay, it can be a CEC of 3 to 100 milliequivalents per 100 grams of soil. Next up, we have pH, and this is the measure of acidity or alkalinity or basicity in a soil. So it's measured on a scale of 0 to 14. 0 is the most acidic, think battery acid. 14 is the most alkaline, think baking soda. Plants typically like a pH of 6.8 to 7.2. That's a pretty small scale though. They will accept soils that are low 6s, high 5s. Anything less than that, you're going to have an acidity or acid tolerant plant growing in it, like blueberries or such, or something like that. pH actually stands for the potential of hydrogen, and hydrogen ions are acidic. And the more hydrogen ions that are present in the soil, the more acidic the soil will be. It's also important to note that pH is recorded on a logarithmic scale, meaning that a pH of 6 is 10 times more acidic than a pH of 7, and a pH of 5 is 100 times more acidic than a pH of 7, pH of 4, 1,000 times, so on and so forth, and then also vice versa on the higher end of the scale when talking about alkalinity. Getting more complicated again is buffering capacity. So we're bringing in a couple different terms here. We have pH, CEC, and OM here. So buffering capacity is a soil's ability to resist changes in pH. So it kind of keeps it neutral, not a true 7 neutral, but a neutral to where plants like it. Plants do like a little bit more of an acidic soil. Soils with high cation exchange and high organic matter and a good balance of clay minerals tend to have a higher buffering capacity. And of course, a neutral pH is what you're aiming for, because on either end of the scale, if it's super acidic or super alkaline, certain micronutrients become more or less available and can become toxic quite quickly. This is another one of my personal favorites, EC, which is called electrical conductivity, and it is a measure of salinity. So EC is how well the soil's water conducts electricity. The more salt that's present in the groundwater, the better it will conduct electricity, and then the higher the EC value will be. So pure water does not conduct electricity very well. Super salty water will conduct electricity better, and they typically measure it through probes or a sled, but we don't need to get into that. So EC is measured on a scale of 0 to 16 plus although any soil that has an EC higher than 8 will be severely challenged to grow anything other than the odd kochia plant. An EC of 8 is typically when you're going to see the white crusting on the soil surface, in my experience at least. And you're gonna have a hard time growing anything there. Soils with high EC tend to have poor aggregation because salt actually causes clay particles to disperse. And this leads to reduced soil aeration, surface crusting, and very, very hard compacted soils when dry. If you've ever been in a field and you've seen the bathtub ring, that white crusting around an ephemeral wetland, big word, but a seasonal wet spot basically, it's caused by salty groundwater coming to the surface through, capillary flow, evaporation, any of that good stuff. The water will evaporate and it'll leave the salts behind. So something that we like to say here at HumaTerra is that salinity isn't a salt problem, it's a water problem. Next up here is base saturation. This is something that's pretty important to know what it is when you're looking at a soil test, especially if you're going to be making a fertility recommendation. It is how much of a soil's cation exchange is taken up by basic cations. So this shows the relative amounts of essential nutrients that are present in the soil, but are bound to those negative exchange sites on the soil soil particle surface. When they're bound to the exchange sites, they will not come off those exchange sites unless they're being replaced by something stronger, and plant roots just can't get that done. So if they're bound, they're not available to plants. And knowing the base saturation is used to determine fertilizer needs and how well the soil can hold and supply nutrients to plants. So an example of some basic cations. So remember, cations are positively charged. Basic are less hydrogen, acidic is more hydrogen. So calcium, magnesium, potassium, sodium, those are all basic cations. And then you do have acidic cations, which are just pure hydrogen and aluminum, for example. So depending what the ratio is of the basic cations and the acidic cations and what your CEC is, that all goes into influencing your base saturation. So we've reached the end of the presentation. I know I didn't cover everything that you need to know, but that might help you get a little bit of a better understanding on how to analyze a soil test report. If you want to learn more about soil microbes, you can visit our website, HumaTerra.ca. There's some great blogs, some great resources there that you can learn. If you want more just general soil science, soil chem, soil physics, physical soil properties, you can go to SaskSys or Soils of Sask. They are great websites that the U of S have developed in conjunction with some other soil scientists in the province. And if you're out of province, we're in Saskatchewan here, but if you're out of province and you want more information on Canadian soils, you can visit the national site, which is called CanSys. Thanks for listening. If you have any questions, you can leave them in the comments below. You can go to our website and send in a request on the forum there, or Google it. Thanks for listening. Bye.